All right, welcome back with another video. In this video, we will look into another important stage, a very important stage, I just say, in the gate level synthesis flow. Okay, and that stage is once you have applied timing, power, area constraints really come what your design needs to have. Then tool does a lot of optimization. Fourth thing I mentioned again as you expect. Timing, pretty obvious, power, area, logic. So think of this. When I explain it during the system Verilog course, I explained that okay, every time you want to build a digital design, what you do is you first create some sort of truth table, and that came in the combinational circuit videos too. From the truth table, you create using K maps or some other theorems. You try to minimize number of terms, or you want to minimize number of gates. So you are manually doing that logic optimization, and you want to make sure the logic is simple enough, because simple enough means okay, it has an impact on timing, power, and area. All the good thing is we don't need to do all that manually. All you do is you code it in a high level language like system Verilog. Remember, we are looking at the example of full adder, and I said okay, add this, and now tools look into this. It will create those truth table internally. It will look at the Boolean equations and it will simplify them, all that thing on a huge adder. In this example, we are looking into just a full adder, but in your real design, you can have a huge amount of design in your RTL, and that's simply not possible for you to manually optimize them. And tool is going to do the restructuring of the logic, optimizing Boolean equation and all that. And whenever it comes with first set and intermediate stage, then it looks into okay, what is the timing constraints, what is the power constraint, what is the area constraints. Sometimes the optimization that is good for timing may not be good for power and area. So it needs to know all those constraints and see, also look at okay, which one I need to favor more. Is it timing, is it power and area? Based on that, it's going to create an optimization. Of course, at the end, it's you who need to analyze and decide okay, you want tool to work more by tweaking things a little bit more, or you're good with it. Rarely it happens that when you push a button, eventually you will have all these files in a tickle file, and you just source that, just execute that file, and all these stages will be done. Really, it happens that what you execute very first time, the data that you get is perfect QR. That doesn't happen. So it's a lot of iterative updates, analysis, and all that. All those people who think that is a push button physical design is not a push button. Maybe for a simple design it is push button, but that's where a good and not so good physical design engineer, you can tell the difference. A good physical design engineer needs to know how to control the tool to do the maximum possible optimization in order to meet these timing constraints that you provided. Sometimes overly aggressive constraint might do a bad job. So it's a balance that needs. So, but anyway, the thing that where I was getting into is that you know some commands. So one is a generic compile or compile ultra. This is a generic magic command. So all you do is you type compile ultra and doesn't give anything, or say compile. Tool will just start spending time. It will go through every path, every logic and all that, and will start optimizing it. And you just look at it and sit there and you see a lot of things being printed on your screen or in your log file, and tool is doing a lot of work there. But isn't that simple? You just put this command, rest of the job is done by tool. Where you can control the tool. How a flow created by Rashid is different from another flow created by John. It could be that two things. These commands, they have a lot of options, and when you look at the manual of it or man pages in the shell, you can do man and this command, or help or this command, something like that, and it will give you all the options and the different values of those options. So using a different combination, different things might produce a very different optimized netlist. And that's where the concept of flow comes in. Okay, for your block, a setting might give you a very good result, but exactly the same setting might not give another person in your team the same kind of QR results. Because the logic inside is very different, and how tool actually optimize that or create that might be very different than somebody else. So creating a blog or as your design specific recipe is always the first part in a physical design. You start with I'm sorry. You start with a skeleton flow, a reference flow, and then you start changing options or different commands that you use, and that might work really good for your design. Another thing you can do is one thing is okay, these options, but you can also use some specific variable. For example, here is the one I use. Doesn't matter what it do, but this one, a lot of these type of variable which has high effort. Okay, true means spend a lot of time on optimizing power. What will happen? It will optimize a lot of time, so your runtime, the time it takes for the tool to do the actual synthesis, will increase because now it's probably doing it inside a lot of iterations. That might have an impact on the timing because now you're focusing on high power. It just sometimes not possible to optimize all timing power area equally. You have to pick, tool has to pick a priority somewhere. So maybe with this one, it will pick the power as a priority and at the cost of timing and area. Makes sense? So these commands, they will give you information about how each command works, but sometimes how these work on your actual design, the only way is to do a lot of trials. And that is always the first component whenever you get a new design. Yeah, you need to do a lot of trials and to build a recipe, to build a flow for your design. So yes, so through some of the variables, application variables, those are called tool application variables, and some of the switches and options, you tweak this optimization and create a recipe for your design. So that's optimization. And next stage is now, by the way, remember this DDC that I said after constraints, you can apply that. You can, after constraints, after optimization, you can have saved this file. You can save it here because it probably spends, so if the design is 500,000 instances, it probably took maybe 6 hours, 7 hours, 10 hours. It will depend what kind of settings you have used. You have used a high optimization setting or you have just normal optimization. So depending on that, it can take a lot of time. So you really what you want to do is save this database as a DDC, for example, so that later on you can recover that. And the cool thing about those DDCs in Design Compiler used to be that it will save all your constraints in it. So you don't need to go back and apply everything and redo that. It will take a snapshot of the state of the database inside the memory and save it. Another thing which we do is a netlist generation. So this DDC I already talked about, but as this netlist is important, this basically, this is the netlist. Remember that one? This is called the netlist. So we need to get this netlist because we need to pass it on to the next stage. We could also pass on DDC file, and the next stage is like floor plan or placement. They can read those DDC files. But sometimes for timing analysis, if you want to do, and we will look into STA separately later on too, you need a Verilog netlist. And for the formal equivalence tool, you need a netlist. So there are some tools which really need netlist, so that you can save it internally. So saving a database and taking a snapshot is super important. And then now you have optimized netlist. You really want to analyze, thoroughly analyze. You want to analyze every aspect of timing, general QR like timing, power, area, and all that. How is area, how is power? There are so many commands that you can use. There are some generic ones that people use for sign up. So you need to have those one anyway, but then you can have a lot of additional scripting or reporting just to save the information, just to report the information, the state of the of the different optimization, you can store it in a different file. So typically in a flow, you will have 10, 15 reports, and you don't need to know every one report, but typically every engineer has some sort of go-to reports to look into. And based on that, they will say, okay, I need to go back, optimize something, or it's good enough for now. So reporting is a super important area. I didn't mention, but going through all these, whenever it does all this optimization and reading and anything, all those log is reports message. Tool will report messages. Typical flow, we want to put all those messages in a log file, and so that after it's done, you first thing you do is before you even do QR, go into your log file and check if there's an error or not. Usually when that error happens somewhere, it will stop. It's not going to do further. But sometimes it just moves on and throws a critical warning. So you really want to understand that critical warning. Understand that and see what that warning does. Is there a problem or not? So going through your, not every time, but maybe you write a script and you just pass that log file to the script, and it just tells you, do you have certain warnings or not, and that is good enough for you. So you don't manually these things, you try to automate things. And probably good idea, I will take a note, automation and scripting is very important in physical design. You want to automate as much as possible. The whole goal is somebody eventually in the final state just run a script and does everything. And a lot of your time, you need to work with these tools in such a way that your valuable time is spent on a critical debug or something new in your design. And most of the things that you can optimize your script. So scripting automation is an important part of your job as physical design person, as synthesis person. Okay, I think that's it. We covered it. Finally, we finished the final stages. So yeah, let's time we will start with standard cell library. Look into it. What kind of information is stored and how to read that, how to understand that better. All right. Till then, see you. Bye.